Hello and welcome to Bit by Bit channel. In this notebook, we continue explaining design patterns by introducing behavioral patterns. Please subscribe, like, and share this video to support this channel. Behavioral patterns. Observer. Notify dependence of state changes. The observer pattern defines a one-to-many relationship between objects. When the subject's state changes, all dependent observers are notified and updated automatically. This pattern helps you decouple the sender from the receivers. The subject doesn't need to know anything about its observers. It just broadcasts a change, and all observers decide how to respond. This is useful in many real-world scenarios, including graphical user interfaces where buttons notify handlers, messaging systems where listeners react to events, distributed systems that trigger updates across components. The observer pattern is also the foundation for event-driven architectures, where components can react without tightly coupling their logic. Now, let's walk through an example in Python to see how this works. Let's walk through the observer pattern. We import ABC and abstract method from the ABC module. Then we define an abstract base class named observer, which inherits from ABC. Inside it, we declare an abstract method called update. Next, we create two concrete observer classes, email subscriber and SMS subscriber, each implementing the required update method. Then comes the subject class called news publisher. It keeps track of a list of subscribers and provides three methods: subscribe to add a new observer, unsubscribe to remove one, and notify, which loops through the observers and calls their update methods. Finally, in the client code, we create a publisher and two observer instances. We subscribe them and send out a message using the notify method. As a result, both subscribers receive and print the message. Using abstract base classes this way enforces structure in your design. It ensures that every observer must implement update, which makes your system more robust, predictable, and easier to maintain. Strategy. Encapsulate interchangeable behaviors. The strategy pattern allows you to define a family of algorithms, encapsulate each one into its own class. Instead of hard-coding logic directly into your objects, you extract behaviors into strategy classes. Then, at runtime, you can swap strategies as needed. This pattern helps you follow the open-closed principle. Your code is open for extension, but closed for modification. It's ideal for cases where behavior changes frequently, such as different sorting algorithms, payment processing methods, navigation or routing modes, discount or tax calculation logic. Let's look at a Python example that simulates a payment system where the payment method is chosen dynamically at runtime. This example demonstrates the strategy pattern with different payment methods. We begin by defining an abstract base class called payment strategy using Python's abstract base class system. It includes one abstract method called pay. We then create three concrete strategies: credit card payment, PayPal payment, and Bitcoin payment. Each one implements the pay method differently, simulating different payment processing behavior. Next is the context class, named shopping cart. This class has a method called setPaymentStrategy, which lets the client assign a specific strategy instance at runtime. Its checkout method then calls the pay method from the currently selected strategy. In the client code, we create a shopping cart. First, we set the payment strategy to PayPal and checkout with 50 units. Then, we switch to Bitcoin and checkout again. Each strategy executes its own logic without changing the cart's internal code. This design keeps each algorithm independent, promotes clean separation of concerns, and lets you add or change behaviors without rewriting the main class. Template method defines skeleton of algorithm. The template method pattern defines the skeleton of an algorithm in a base class. It allows subclasses to override specific steps without changing the overall structure. This approach promotes code reuse, ensures consistency across implementations, and makes the algorithm easy to extend. In this pattern, the base class contains a template method that defines the steps of the process. Some steps are implemented directly, while others are left abstract for subclasses to define. The template method pattern is useful when you have common workflows, lifecycle methods, or multi-step operations where most steps stay the same, but a few differ between use cases. Let's see this in action with a document generation system where the structure stays the same, but the content format changes. This code demonstrates the template method pattern through a document generation system. We start with an abstract base class named Document Generator. It defines a method called GenerateDocument, which outlines the full process: open file, write content, save file. The open file and save file methods are implemented in the base class, because those steps are the same for all document types. But write content is marked as abstract using the abstract method decorator. This means each subclass must provide its own implementation. We then create two concrete classes, PDF Generator and Word Generator. Each one defines how to write its own specific content. In the client code, we create a PDF generator and a Word generator. When we call GenerateDocument, both follow the same process: open file, write content, save file, but the content writing step is unique to each class. This shows how the template method pattern lets you keep shared behavior in the base class while allowing flexibility in the variable parts. Iterator, sequential access to elements. The iterator pattern provides a consistent way to access elements of a collection sequentially without exposing its internal structure. This pattern separates traversal logic from the collection itself, allowing the same iterator to be used with different collection types or different iteration strategies. Iterators are widely used in Python, and the language has built-in support through the _iterator and next methods. You can use this pattern when you want to give users the ability to step through your custom data structures using a for loop or other standard iteration mechanisms. Now let's build a simple iterator for a custom collection class in Python. This code demonstrates the iterator pattern with a custom book collection. First, we define a class called Book Collection, which holds a list of book titles and has a method to add books. To support iteration, it defines a special method called _iter, which returns an instance of a custom iterator class named BookIterator. The BookIterator class is where the actual traversal happens. It stores the list of books and keeps track of the current position using an index. It defines two special methods, _iter, which returns itself, and _next, which returns the next book in the list. If the index reaches the end of the list, it raises stop iteration, which signals that the loop should end. In the client code, we add 3 books to the collection and then loop through them using a standard for loop. Even though our collection is a custom object, it behaves just like a built-in iterable because we implemented the iterator protocol. This pattern is useful when you want to give users controlled, consistent, and safe access to items in your collection without exposing the internal data structure. Command: encapsulate the request as an object. The command pattern encapsulates a request as an object, allowing you to parameterize, queue, log, or undo operations without tightly coupling the sender to the receiver. This means the class that invokes an action does not need to know the exact logic or class that performs it. Instead of calling methods directly, the sender uses command objects which wrap both the action and the receiver. This pattern is useful in many situations, such as GUI buttons, remote controls, task scheduling systems, and undo-redo operations. Let's look at an example where we use command objects to turn devices on and off using a remote control interface. This code demonstrates the command pattern by modeling a remote control for turning a light on and off. First, we define an abstract command interface with one abstract method called execute. This defines the common interface all command classes must follow. Next, we have the receiver class called light. This class has the actual methods for turning the light on and off. We then create two concrete command classes, turn on command and turn off command. Each of them stores a reference to the light object and implements the execute method to call the appropriate action on the light. Now comes the invoker, called remote control. It stores a command and has a method called press button, which simply calls the command's execute method. Finally, in the client code, we create a light instance, wrap it with two command objects, one for turning it on and one for turning it off, and assign them to the remote control one at a time. Each time we press the button, the currently assigned command is executed without the remote needing to know what the command actually does. This pattern lets you fully decouple request senders from the logic that performs the request, and makes it easy to support queuing, undo operations, and command history. Visitor operations on elements of an object structure. The visitor pattern allows you to add new operations to a class hierarchy without modifying the existing classes. It separates the algorithm from the data structure by placing the operation inside a visitor object. Instead of adding methods directly to the element classes, you pass a visitor object to each element, and the element then delegates control to the visitor's method. This is especially useful when working with complex object structures such as syntax trees, document structures, and compilers, where you often want to perform many unrelated operations on the same types of elements. Let's walk through a simple example with shapes. We'll define a visitor that calculates the area of different shapes without changing the shape classes themselves. This code shows the visitor pattern in action by computing the area of different shapes. We start with an abstract base class called shape, which defines an accept method that takes a visitor. Two concrete shapes implement this interface, circle and rectangle. Each one implements the accept method by calling a specific visit method on the visitor object, passing itself in. Next, we define a shape visitor interface with two methods, visit circle and visit rectangle. This interface declares what operations a visitor can perform. We then create a concrete visitor called area calculator. It implements the visit methods to calculate and print the area of each shape. In the client code, we create a list of shape objects and one visitor object. For each shape, we call its accept method, which delegates the operation to the visitor. Notice how the area calculation logic is completely decoupled from the shape classes themselves. This makes it easy to add new operations like drawing or exporting without touching the original shape definitions. The visitor pattern is a great fit when you need to perform many operations on objects in a class hierarchy without changing those classes. Chain of responsibility. Chain of handlers. The chain of responsibility pattern lets you send a request through a chain of handlers until one of them handles it. Each handler either processes the request or passes it to the next handler in the chain. This pattern helps you decouple the sender from multiple possible receivers and avoids tightly coupling the request logic to any single handler. It's commonly used in event handling systems, middleware pipelines, validation chains, and logging frameworks, where you want multiple components to have a chance to respond. Let's see an example in Python where we use this pattern to build a simple support system with 3 levels of help: basic, intermediate, and advanced. Let's walk through this chain of responsibility code step by step. We start by importing ABC and abstract method from the ABC module, which lets us define abstract base classes. We create an abstract class called handler. This will act as a base for all our support levels. Inside it, we define a constructor that initializes an attribute called nextHandler. This will point to the next object in the chain. We also define a method named setNext, which allows us to link one handler to another. It sets the next handler and returns it, so we can train multiple calls like a .setNextB.setNextC. Then we declare an abstract method called handle. Each concrete subclass must implement this method to decide whether it can handle the request or pass it forward. Next, we define our 3 concrete handlers: basic support, intermediate support, and advanced support. Each of these classes inherits from handler and overrides the handle method. In basic support, we check if the request is equal to the string basic. If so, we print a message saying it was handled. If not, we check if there is a next handler. If yes, we forward the request using self.nexthandler.handle. We follow the same pattern in intermediate support and advanced support, but each one checks for a different keyword, either intermediate or advanced. Now, in the client code, we create instances of each support level. Then we link them using setNext, so the chain becomes basic, then intermediate, then advanced. Finally, we test the system by calling basic.handle with different types of request strings. First, we send in intermediate. Basic support can't handle it, so it forwards the request to intermediate support, which handles it and prints a message. Then we try advanced. The request goes from basic to intermediate to advanced, and finally gets handled by advanced support. Lastly, we send in unknown. None of the handlers know how to handle it, so the chain ends and we print a default message. This design gives you flexibility and decoupling. You can add, remove, or reorder handlers without changing the sender code or the core processing logic. This is why the chain of responsibility pattern is widely used in event pipelines, web request middleware, user input validation, and logging systems. Interpreter. Define a grammar and interpret sentences. The interpreter pattern is used to define a grammar for a simple language and interpret sentences built using that grammar. It works by representing each grammar rule as a separate class in a class hierarchy. These classes together build an abstract syntax tree, or AST, that represents the structure of the input sentence. The pattern then interprets or evaluates the tree using recursive calls. This design is especially useful when building simple interpreters, expression evaluators, rule engines, or domain-specific languages where you need to evaluate structured input. Let's see a Python example of the interpreter pattern by evaluating arithmetic expressions using class-based rules. This example shows the interpreter pattern being used to evaluate a simple arithmetic expression. We begin by defining an abstract base class called expression. It has a single abstract method named interpret. Each subclass will implement this method to perform a calculation. Next, we define a terminal expression class called number. This class represents simple numbers. It stores a value and returns that value when interpret is called. Then, we define non-terminal expressions, one for addition and one for subtraction. Each of these takes a left and right expression as input and recursively calls interpret on both sides, combining the results with either addition or subtraction. This design allows us to build expressions like a tree. For example, one expression can contain another expression as its left or right part. At the bottom, we create an expression tree that represents the formula 5 plus 3, then minus 2. We do this by nesting the class calls. First an add between 5 and 3, then a subtract between that result and 2. Finally, we call interpret on the whole tree. This triggers a recursive evaluation from leaves to root, and we get the result, 6. This is a textbook use case of the interpreter pattern. It's perfect for building mini interpreters, calculators, custom rule engines, or domain-specific languages where you define and evaluate grammar rules in a structured way. Mediator. Reduce direct communication between objects. The mediator pattern centralizes communication between multiple objects, also called colleagues. Instead of talking to each other directly, they all interact through a central mediator object. This reduces the dependencies between components and makes the system more flexible and easier to maintain. If components communicated directly, changes in one object could force changes in many others. With a mediator in place, each object just talks to the mediator, and the mediator decides how to route the interaction. This pattern is useful in situations like chat systems, graphical user interfaces, control panels, or anywhere multiple objects need to coordinate without becoming tightly coupled. Let's look at an example where multiple users communicate through a chat room mediator. In this example, we implement the mediator pattern using a simple chat room system. We begin by creating an abstract base class called Mediator, with an abstract method named send. All mediator implementations must define this method. Next, we define a concrete mediator class called chatroom. This class maintains a list of users who join the room. The register method adds a user to the list and sets the user's mediator to this chatroom instance. The send method loops through all registered users. If the user's not the sender, it calls their receive method to deliver the message. We then define a user class, which acts as a colleague. Each user has a name and a reference to a mediator. When a user wants to send a message, they call their own send method, which prints the message and passes it to the mediator. The mediator then handles distributing the message to other users. In the client code, we create a chat room and 3 users, Alice, Bob, and Carol. We register all users to the chat room, and then Alice and Bob send messages. As you can see from the output, when Alice sends a message, Bob and Carol receive it. When Bob replies, Alice and Carol receive his message. Importantly, none of the users talk to each other directly. All communication goes through the mediator, the chat room. This reduces the dependencies between users and makes it easier to manage and extend the system. This design is perfect when you want to control or coordinate interactions between objects in a flexible, centralized way. State. Change behavior based on internal state. The state pattern lets an object change its behavior based on its internal state. Rather than using large conditionals, like if-else or switch statements, you encapsulate each state in its own class and delegate behavior to that state. This keeps your code organized, flexible, and extensible, especially when the logic for each state is complex. The context object maintains a reference to a current state, and it delegates requests to that state. The state itself can decide when to transition to another one. This pattern is useful in workflows, UI components, game development, or protocol handling, where an object behaves differently depending on its mode or phase. Let's look at a Python example of a document that behaves differently depending on whether it's in draft, moderation, or published state. This example demonstrates the state pattern through a simple document publishing workflow. We start by defining a base abstract class named state. It has an abstract method, publish, which each concrete state must implement. Next, we create 3 concrete states: draft, moderation, and published. Each class defines its own publish method. The draft class moves the document to moderation by calling context.setState and assigning a new moderation instance. The moderation class represents a review phase. It transitions to published when approved. The published class prints a message but doesn't change the state any further. The document class is our context object. It holds a reference to the current state, starting with draft. Its publish method simply delegates the call to the current state object. In the client code, we create a document and call publish 3 times. First, it moves from draft to moderation, then from moderation to published. Finally, since it's already published, it prints a message and stays in the same state. Notice how the context delegates behavior and how each state class defines what happens next. There are no if-else statements to check the current state. This makes it easy to add or modify states later without touching the rest of the code. This pattern works well when an object's behavior needs to change over time in response to its internal condition. This table summarizes the behavioral design patterns we've covered in this chapter. Each pattern focuses on how objects interact and distribute responsibilities based on runtime behavior, state, or control flow. First, the observer pattern lets objects get notified when another object changes. It's used in event systems, GUI apps, and reactive programming. The strategy pattern makes it easy to switch behavior by using different strategy classes. This is common in sorting, algorithms, or pricing systems. Template method defines the skeleton of an algorithm and lets subclasses override parts of it. You'll see this in report generators or parsers. The Iterator pattern gives sequential access to elements, especially for collections, files, or custom data structures. Command pattern encapsulates requests as objects. It's essential for implementing undo, remote execution, or task scheduling. Visitor pattern separates operations from objects they act on. It's useful in compilers, document formatters, and abstract syntax trees. Chain of responsibility passes requests through handlers. Each handler can deal with the request or pass it forward. This is commonly used in logging systems, event handling, and web middleware. Interpreter defines grammar rules and evaluates expressions. It's used in small languages, calculators, or domain-specific configuration systems. Mediator pattern removes tight coupling by using a central object to coordinate communication. It's helpful in chat applications, air traffic systems, or complex user interfaces. Memento pattern helps you save and restore state, perfect for implementing undo, redo, or versioning. And finally, the state pattern allows an object to change its behavior based on its internal state. This keeps logic clean in games, user interfaces, or multi-phase workflows. Together, these patterns help manage complexity in systems where behavior changes dynamically or multiple objects need to cooperate cleanly. Thanks for watching.